A2 Maths, Iterative Methods. Right, so what I'd like you to do is I'd like you to start with this function just here, naught equals 3x cubed plus 2x squared minus 4x minus 2. And I'd like you to just rearrange it to show that it can be rearranged to each of these three separate equations. Okay, so just pause there, have a go at rearranging that equation and think about how you do it to get to each of those three. Okay, so let's see how you got on then. So this first one, so we noticed that some parts of it are very similar, like you've got 3x cubed plus 2x squared minus 2. It looks to me like the minus 4x is missing out there. So what could I do? I could maybe add that 4x to the other side. So that's what I'm going to do first of all. Then once I've added 4x to the other side, to get x on its own, I could just divide by 4. So it's the same equation. Those two equations are absolutely identical to each other. It's just a different rearrangement. Okay, so have a go at the second one. They look almost the same. Actually, not quite, is it? This number here was 4x minus 4x. Now it's minus 3x. So what could I do to get from minus 4x to minus 3x? If I add x to both sides, then straight away that equation is sorted. So that's a very easy rearrangement. I just added x to both sides. So there's nothing wrong with doing that. With this one then, starting off with that equation again, think about the parts that are already sorted. Look the same. Well, actually, it looks quite similar, except it's the opposite signs, isn't it? So the 4x has changed sign. Minus 2 has gone to plus 2. The positive 2x squared goes to minus 2x squared. So these seem to have changed sign. So what I'm going to do is I'm just going to start by taking everything to that side. So therefore, I can change those sides. So I've taken everything to the side, but then I've flipped it around. So just make sure you're happy with that. So there we go. Once I've done that, I can get rid of the 3 by dividing by 3. That gets me a third of it. And then I can get rid of the cube by doing a cube root, and therefore I get down to that equation. Right, so having the ability to rearrange that equation equaling 0 just to different equations where you've got x at the start is the first part of being able to use what we call this iterative method. Right, so what I'd like to do, please grab your notebooks. The iterative method, this method rearranges any function that's equal to 0 to a form where x equals some function. So that's exactly what we just did. We started off with 0 equals some sort of function, but we rearranged each of them so that they had x equals some other function. Now they're the same, they're exactly the same. So if I took x away from that, g of x minus x is just f of x. So they're absolutely identical, but having it in this form will help us do the iterative method. So what we're going to do is, because we've got it in this sort of format, we can work out an iterative formula by just replacing the x inside the function for xn, some value, some guess an x value, and then when you put it through this function g, what you end up with is another value of x, which is hopefully an improvement. So for example, that previous one we just looked at, we saw that we could rearrange it like this. Okay, so we rearranged that previous example to get to like this. That was the one where we just added x to both sides. And now because we've got x equals some function, what we can do is we can replace the x's on this side for xn. There we go. And they equal xn plus 1. So they're different values of x, but as we'll see, they are a better approximation. So what I can do is I can substitute in some value, x0 being the very first value, some sort of guess that you might have to start with, which is some sort of approximation of the root. So you might look at this and you might go, I think the solution to that bit, obviously with x added onto it, so some solution might be x equaling 1. That would be your first guess. And what you would do is you would take that x1 and you would substitute it into there, and there. You would calculate it, it would work out a value, and that would be your next x value. So after I substitute 1 into it, out would come another value. Now 1's not going to be any good, you can put it in, you can see why, but 1.5 for example, I'll stick 1.5 into there, see what I get, and the answer I get will be a better approximation. If it works, that is. Sometimes it doesn't work, but if the iterative formula works, then what we notice is the x1 is a better approximation to the root, the solution to the equation, than the first one we substituted in. Now what we can do is we can carry on following that through. That's where the word iterative comes into it. We've done it once and we could just keep going until we're happy that we've got an approximation to as many significant figures as we need. So I could substitute in this next value that came out when I substitute x naught in. I could substitute that back into there, and there. And what I end up with is another value that comes out, and that will be another approximation that will be better than that one, which was better than that one. So it's improving every time. And we can just keep improving that until we get the root as accurate as we want. Okay, so pause there if you want to take any notes. Right, so write this question down in your notebook. So show that the equation 3x cubed plus 2x squared minus 4x minus 2 equals 0 can be written in this format, and use the iterative method to show, using the initial one to find a solution to three significant figures. So I'm looking for a solution to this cubic equation just here. It doesn't factorise nicely, so the roots aren't going to be nice numbers. So what I'm going to look for is an iterative method that could hopefully estimate some of those roots for me. Right, so just pause it there, write down what you need, the question, have a go yourselves if you want to first of all, and then we'll have a look at putting the model solution down in our notebooks. Okay, so let's see what we need to do. So for part A, we practice this just at the start of this lesson, where we just want to show how to rearrange from that to that. How can you get from the equation equaling 0, which is the equation we're trying to solve, to a different way of writing it? So it's the same equation, but just in a different way with x equals some function of x. Okay, now you could do this one fairly easily. We could look at adding 4x to both sides and then dividing by 4. All right, so we've seen that one already, but show how you do it step by step, ready for that exam. Right, so once I've got it in this form, I can now write out my iterative formula. That's what I'm going to do now. So for part B, I can rewrite this equation. So even if I couldn't do the first bit, it doesn't mean I can't do part B. I can take that equation, I can replace the x for xn, and once I've done that, this side of the equation, x on its own, will be my next value up. So there we go, I've got my iterative formula, I'm ready to use that. I just need a starting value, which can be x naught, which is given to us there. So my first approximation, someone's come along and said, my guess is x equaling minus 1. You sub x equals minus 1 in there, it clearly doesn't equal 0. So what I can use is I can use this iterative formula to improve that x equals minus 1. So if I substitute it into our iterative formula here, okay, so I'm substituting it in there, I calculate this value just by number crunching on my calculator, out comes minus 0.75. Now minus 0.75 is a better approximation of the root. If I put minus 0.75 in here, although it doesn't equal 0, it's closer than minus 1 was. All right, you could try it yourself. Substitute both of those in and you'll see that this is a better approximation. But it's still not good enough. What I need to do is I want to improve it further. So I'm going to stick minus 0.75 in now. I take that, I put it in where xn is, and that's going to give me another solution. So there we go, I've substituted it into both of those places, and out comes minus 0.5352. Now if you take that value and substitute back in the original, you would see that although it doesn't equal 0, it's getting a lot better, it's getting a lot closer. It's certainly closer than that one and that one. Okay, what do? You keep going. Now we need to get to 3 sig figs. So I need to get it so that I have 3 significant figures repeated so that I'm confident that the actual final answer is to 3 significant figures. So let me just go through and double check that. So continue with the iterative formula. So take that value, substitute it into there and there, press your equals value, and out comes this. Now, a bit of a trick on your calculators is what you can type in is type in the first value equaling -1 and press the equals button. Now, the moment you press the equals button on your calculator is that sets your calculator up so it knows that -1 is an answer. Then what you can do is you can type this function in here, 1/4 lots of 3. Now, instead of putting -1 into it, just here for xn, use the ans button on your calculator, the ans button. And what that will do is the calculator then will replace that for -1 cubed plus 2 lots of ants squared minus 2. And when you press equals, out will come another answer. Now, if you keep pressing equals, what will happen is the answer that came out will go back in for the new ants. And so you can keep getting all these values without having to type it all in. Okay, so have a go at doing that yourself. See if you can work out what I mean. If you can't, you can always ask your teacher. Right, so calculate the iterative formula. So take that value, substitute it in. Out comes 0.4718. Still nowhere near 3 sig figs. Try x4, 0.4675. That's looking a bit better. In fact, they're the same, aren't they? Two significant figures. Those two. Try these ones. Well, those two are almost the same to 3 significant figures. 0.468, 0.467. So if I try the next one, there we go, minus 0.467 as well. I'm confident that now, because these two go round to 0.467, your final answer to 3 significant figures will be minus 0.467. So there we go, minus 0.467. You've got to keep going until, not here, right, that's where you might get checked out by the examiner because they look the same, 0.467, 0.467, but you need that one just to verify that you've got two that round to the same amount of significant figures. Okay, right, so this equation has 3 roots. We know that because it's a cubic equation. So it's got 3 roots. Some of those could be non-real, but let's just go with the fact that this has got 3 real roots. Now, when I use this formula just here, if you try some different starting values, so instead of -1, you could try some different starting values, and hopefully that will help you find the other roots. So what I'd like to do is just try that. Try some different starting values. Instead of -1, try 7, try -13, try whatever values you like. See if you can, when you keep pressing the button on your calculator, see whether it finds those other values for me. Okay, so pause there, take some values you like, any values you like, stick them in there and see what values you come out with, and see if you can find the other roots by sticking in some new x naughts. Okay, so pause, have a go at that yourself. Okay, so hopefully what you found is that when you put some of those values in, sometimes what happens, for example, when x naught equals 2, you've got this sort of situation. So the next value was 7.5, so clearly a big improvement there. But then the next value was 344, and then the next value was something ridiculous like that. What's that? 30 million. Okay, so you're in a situation where the whole thing is just blowing up. It is diverging. So sometimes, and this is what I meant from that second slide, saying if the formula works. Now in this case, it didn't work because the solutions diverged. We know it can work because when we substitute -1 in, we clearly were targeted on a root. But some values of x naught do not work. They diverge, so therefore that does not help us find a root. So we just try a different value. Now, it doesn't matter what value you tried, none of the values would go to the other 2 roots. So the question I would ask you is, how can we find the other 2 roots if this iterative formula didn't work? It either diverged or it just kept focusing on the same root. What would you do? Well, of course, the answer would be trying some different iterative formulas. This was just one example we looked at. You saw at the start of the lesson, there was lots of ways of rearranging this formula so that it was x equals. Okay, this one was the one where I took the 4x to the other side and divided by 4. I could have one where I take the x squared over the other side, half everything, and square root. That would be a perfectly reasonable iterative formula. that you could use. You could have one where you just add x to both sides. That would work. Now, some of those might find the other roots, some of them might not work at all, and some of them might just find the same root. You've just got to play with them and see. So in the case where you need to try a different iterative formula, you need to try something different. Right, so what I'd like you to do, please, just practice some of those skills. So if you go to exercises 2.1 and 2.2, have a go. Most of them are sort of rearranging to get to an iterative formula, and then just trying to use the iterative formula to find a solution. Okay, so you've used the iterative formula to find roots. Let's just have a look graphically about why this actually works, what this actually does. So what I'm going to do is I'm going to plot down on that graph two equations. The first equation I'm going to plot down is, once I've rearranged, I'm looking at the f of x. Now in the previous bit we called that g of x. Doesn't matter, it's the same thing. So I've rearranged an iterative formula and I've got some function equals x. And what I'm trying to do is I'm trying to find where these two equal each other. So what I'm going to do is I'm going to plot both those curves. So if I plot the two curves, the f of x curve, all right, looks like that. So it could be any curve you like. There we go. That's my graph of some function of x. The other graph is y equals x. So that's on the opposite side. So look what I'm doing. I'm drawing a graph of this side equals y and this side equals y, so that I can start to think about where these two solutions are. Now these two solutions, where these two graphs cross, are the solution to the equation if this was just equaling 0. Imagine if I took that x away from that side, I'm looking for where they equal 0. So if I can find where they intersect, that would be the solution to the original function. That's what the iterative method is trying to do. So what do I usually do then? Well, I usually start with some number, x0. Okay, so I'm given an x0 value. And I start by taking that x0 and putting it into this function here. This function has usually got xn's in. So I take my x0 and I substitute it into the function. That's importance. Now, once I've substituted into that function, that value becomes my next x value. That will be my xn plus 1. So I've substituted it into there. I've got this value out, whatever it is over here, and I use that for my new value. So what I do is I can put that across, and that would give me my next value of x. Now notice it's going away from this root, but hopefully it's going to start targeting on this route. I'm looking for it to get closer and closer to a certain value. So although it's not focusing on the nearest route, it will hopefully end up focusing on this one. So what happens then? So I get my x1, and now I repeat the process. I take my x1, I substitute it into the function again. So I substitute it in, there we go. And once I've substituted it in, that becomes another new x value. So I'll take my answer from that, and that will become my new x value. There we go. And that will be x2, which is a closer approximation to this root than that one was and that one. Right, so I carry on the process. This x2, what do I do with it? I substitute it back into the function. So I'm going up to the function. And then once I've gone up to the function, that's going to give me my new x value. So I can go across, and that would give me x3. And so you get into this pattern where you go up to your function, across to your y equals x, up to your function, across to your y equals x. Sometimes you go down, but you're thinking up and down to your function, across to your line y equals x. And as long as you remember it that way round, you'll be fine. Where people make the mistake is they start to think, I'm going to go up to the line y equals x and across to the function, and then the whole thing goes a bit pear-shaped. So you must remember it the right way around. But the idea of understanding where you put it into the function will help you with the graph. You take your x0 and you substitute it into the formula part, the curve. That becomes your new x. Substitute that into the formula. That becomes your new x. Into the formula becomes your new x, and we can carry that on. And as you can see, that once you get to x4, it's getting very close. Look at the steps. Okay, so the approximation is improving, but now it gets really, really close to this point just here, to the point where we can't even see it anymore. Now that diagram just there, so grab your notebooks, make a quick sketch of it. If you've got a situation where you're going like that, and you're stepping closer and closer, that is what's called a staircase diagram. Okay, so we get a situation where we form this sort of staircase, and that's usually because you have a concave section like that. Because we've got a concave section, then we're going to have this staircase diagram coming like that. So pause there, I'll do the sketch, get the name down in your notebooks before you move on. Okay, so we're going to repeat the same idea, but this time when I draw the graph, we're looking at it more in that sort of situation. So it's still a concave section, but it's the one that's going downwards. So we're looking at that. And what's going to happen is we're going to put our line y equals x in. There we go. And we're going to do the same sort of thing as before. So I'm going to take my x naught, some value down here somewhere. And what do I do with that x naught? I substitute it into the function. So I just go up to the function. From there, I repeat the same process as I did a minute ago. So I go up to my function. That becomes my new x value. So I can go across to my x value. That will tell me this value just here. Now, normally you would have these two values already calculated, so you will know if you're in roughly the right situation. Now, look what happens here though. Once I've got that, I substitute that value into my function. So I draw it down to that line. From there, that becomes my new x value. So unlike before, we can clearly see it's not a staircase diagram. That becomes our new x2. And what you're doing here is you're sort of flicking from one side of the root to the other. So the x0 became the x1, which goes back to the x2. And we're sort of flicking around to this root just here. This is the solution to the original graph where those two intercept. So what do I do? From there, I can go up to my line, I can go across to my x, and so on. So we end up with x3 being on that side. But notice that although they might be on opposite sides, they are clearly getting closer and closer to that approximation. So my sketch starts to look like that. And there we go to x5. Now that diagram, as you see, is clearly not a staircase diagram, but the way it's sort of spiraling in gives its name a cobweb diagram. Okay, so again, do a quick sketch, take in whatever notes you need. Sometimes you might have a situation where the whole thing just diverges though. If you go up, in this situation, everything will focus in, but sometimes you might have a situation where you go up to your line, you go across, so you go up to your function, across to your line, and you find that the whole thing just keeps blasting off and getting bigger and bigger. So it can diverge. It doesn't always get a staircase or a cobweb diagram. Okay, but if they do target on a route, then they end up being one of those two. So what I'd like you to do then, please, have a go at the exercise 3.1. It'll involve you making sure you can sketch some cobweb and staircase diagrams. This came up for on the very first exam paper. The students were expected to draw a staircase and cobweb diagram, so you will get it in your exam. So it's important to make sure you can do these sorts of questions.